Hi, I'm Matt with Flexxbotics, here with a demonstration of the Flexxbotics software solution. I'm going to be walking through our control software on my Chrome browser. This is a centralized configuration and control hub supported by distributed or virtualized edge instances that feed live data into our control plane. It's deployable in the Flexbox cloud, your cloud, or on premises. We are looking at that control plane now, with each of these entries representing a work cell consisting of one or more live connections to real devices. This is the digital foundation of our platform. Read-write, live connectivity to any number of OEM devices, PLCs, sensors, and industrial machinery. This tour is going to start with configuring connectivity and mapping processes onto variables. From here, we'll use those variables to inform overall production monitoring as well as detailed process monitoring. We'll close on our unique capability to act on this monitoring via closed-loop autonomous process controls. Flexbox connectivity is driven by what we call transformers. These Python-based modules handle read-write communication to a wide variety of device types, utilizing low-level protocols and common architecture to access runtime data, contextualize it into useful, legible information in real time, as well as route it to both Flexbox destinations and external IT. You can see here in our Device Manager's Transformers tab, we can read, modify, and expand on these transformers in a fully functional IDE environment, complete with tooltips, IntelliSense, and revision control. The Device Manager is our interface for deployment. You can see here we already have created devices for a number of work cells within our facility. Each work cell here represents a containerized runtime physically connected to each device represented. Once edges are deployed and connected to the platform, we can assign device transformers by punching in the correct make, model, and controller type, as well as do some basic networking information configuration. We can also sync every device with its latest transformers as they are developed, and verify the health and log output of each of these devices from the Health tab. Now that we've covered how to configure connectivity to these devices, let's head over to Run Configurations and see how we can organize and contextualize the data we are pulling off of each asset. If we crack open the G9 cell, we can see that we're tracking a variety of data across a number of sources. Our TCP data transformers collected and collated data from a digital gauge and other sources and mapped it onto a number of different critical features. Similarly, we have live runtime data from our CNC and FANUC robot, collected at different frequencies and tied to specific tools and operations. All variable data is collected based on data events generated in real time, organized by work order, device of origin, and with respect to specification and control limits. Making new variables is a straightforward process, and we provide templating tools to both generate variables and also distribute them across different similar cells in mass. You may have noticed that these variables reference both part features and tooling. These associations are assigned here at the run configuration level, and they allow us to collect events like feature deviation and tool breaks to specific runtime events. While we have a single run configuration for each work cell in this example, variables can be further specialized to be specific to individual parts, operations, and tool configurations. When I deploy platform, I work with customers to determine what level of granularity is needed based on the product, process, and desired outcomes for that data. For example, if someone is trying to implement production monitoring and is only looking at a few QA results, only a few variables in a single run configuration might be needed. If the process changes greatly between changeovers or between parts, and those changeovers are frequent and more comprehensive, more run configurations might be needed to capture that granularity. No matter how they are implemented, these contextualized variables make up the baseline for any advanced manufacturing process and can drive any visualization or control effort. All data that moves through the Flexbox platform is collected and organized with production context in mind. Part rates, cycle times, and uptime data are all collected and evaluated through this framework. Our factory view here gives you production metrics at the plant level, characterizing both part production rate and uptime. We find that part rate is very useful to many platform users, as it can be used to quickly evaluate whether production is meeting quoted targets and whether orders are consistently exceeding projected labor or machine time costs. That's why we build granularity into this view. It allows us to filter by site, work area, and specific work cell, exposing specific information as to which cells, areas, or individual parts are lagging behind targets or experiencing unplanned downtime. We can drill down one more layer by opening the work cell view. Here, we can see week by week utilization and production yield. Notice that in both views, we're using contextualized data to drive specific downtime reasons and failure modes. These results are composited from multiple variables and machine feedback as well that are processed by the system transformer. For example, we can highlight that a reject was being caused by oversized stock based on both robotic gripper feedback and machine probing. Or perhaps we can identify when a machine has a coolant failure, not from a specific machine alarm, but by noting coolant pressure dipping for more than 10 minutes. We can demonstrate while this demonstration is covering a machining environment, the platform can contextualize downtime from a number of different processes and parameters. An injection molding example might be a short shot failure, where a lack of injection is was feedback pressure is recorded and noted. A press or stamping example could be when a die is wearing thin from by measuring peak tonnage per stroke climbing steadily across an individual shift. This kind of data insight helps manufacturers identify production issues quickly and with accuracy, while defining exactly how those problems could affect profitability and output. Process data is also collected and organized in the Flexbox platform. The process variables screen is a great resource for turning runtime and inspection data from work cells into action on the floor. Here, we can select a work cell and a run configuration, as well as a date range, and pull up a complete list of process variables, complete with control limits and CPK calculation. This view allows us to investigate variables associated with specific tools, orders, and critical features from a given time frame. I can line up and compare variables as well, honing in on relationships across data and drawing trends between process behavior and QC outcomes. The platform also supports work order traceability, allowing you to pull up and search for orders. Clicking into one record, you can see related process variables as well as quickly access production data from the relevant time period. Many customers can spend hours upon hours a week combing through data like this, trying to trace back quality events through dense production data to identify links between process behavior and quality outcomes. Flexbox utilizes our active escalation view to automate this forensic process. You can see here that we've set up statistical rules for individual variables or groups of variables that trigger a centralized notification packaged with all the supporting data, ready to go. These rules can be made individually or in bulk. Adjusting rules can be done on the fly as you get a handle as to which escalations require action. Let's work through an example on cell G9, a cell managing bearing components. If I filter here, I can see two active escalations related to G9. Both clearly indicate which feature is seeing a problem and the work cell involved. If we click into our QC issue tool, we can see highlighted the triggering trend. Let's imagine a scenario. Tool wear on the boring bar is built up gradually across a shift. By the time bore diameter actually hits the control limit, the machine had already begun running bad parts. If you look at these diameter readings, there's a clear drift. And when you overlay tool 4's axis load and temperature, you can see that signal was already there. The boring bar was wearing, the axis is working harder to compensate, and heat is building. As a result, you're going to get a dimensional drift. In a traditional setup, it's hard to see this until a part actually fails gauge. By then, you've already produced scrap, you might have a machine down, and you're doing a root cause analysis. Flexbox connects these signals preemptively. The load, temp, cycle creep, and bore are all correlated, time-stamped, and in one place. You don't need to go hunting across 3 systems to build that picture. Our second example is a little bit more proactive. We are looking at a mean deviation that might precede a control limit breach. The parts are still in spec, but the last 7 wall thickness feedings are above the process mean, trending up. Now look at what that machine was telling us at the same time. We have a z-axis temperature climbing, we have a coolant temperature climbing, so it becomes a pretty clear story. The spindle is thermally loaded, and the part geometry is drifting. This escalation fired before the part was out of spec. That's the difference between catching a process drift in real time versus scrapping a batch. Flexxbotics was watching that pattern. The rule fired and the escalation opened, and now a process engineer can make a call, adjust the coolant flow, flag the tool for inspection, or schedule a compensation offset. There's now an opportunity to fix this before it becomes a true production problem. With some iteration, many customers are able to tune these rules to become increasingly specific and eliminate noise. Over time, these escalations don't just catch processes that have broken compliance, but they start to trigger in advance of those issues and provide tools to correct before any scrap or downtime has occurred. Before we wrap, I wanted to highlight another capability. Flexbox read-write access to machines can work together with our active escalation feature to create a closed loop, where trends and runtime data are corrected with variable adjustments right from the cloud platform. We call this autonomous process control. We can enable this feature for any individual escalation or group of escalations from the correction field. Once active, it's possible to prompt the user for manual adjustment on any variable or execute an algorithmic adjustment embedded in the Flexbox transformer methods. Our customers tend to go through a progression with autonomous process control. They start collecting data and they establish control limits using our SBC tools. They might then set up some basic rules to catch trends towards limits or flag limit breaches, dispatching folks to make adjustments and bring processes back into line. From there, they might send up human in the loop autonomous adjustments, implementing manual and transformer calculated suggestions. And if the process is a fit, you might be able to implement fully autonomous correction for those variables and limits that are best suited to closed loop control. With this, skilled production managers can focus on new and emerging products and problems and automate the handling of well characterized error modes using the Flexxbotics platform. This concludes our demonstration. Thank you so much and have a great day.